Hello everyone, it's Quick Flash back with another video, and today I'm going to be discussing the motor mix, the mixer code, and why the old mixer, or the current mixer in EmuFlight and betaflight, has some problems and how a new mixer can help solve that. So you can see the graph on the top, that shows the Z direction, so up and down. That direction shows the motor output based on the motor mix delta, which is the difference between two motors, and your throttle. And as you can see, this is not a smooth graph. It's somewhat jagged and it's not smooth. However, you can see on this bottom graph that there is a way to smooth out the motor outputs for, a quadcopter, and that all has to do with the mixer. And I'm going to talk about the mixer today and why this bottom graph is so much better, and some ways in which we can achieve that. So to start out, I'm going to hop in the code and show you what the mixer is. So for all of you guys, PI and D should be fairly simple terms. Roll, pitch, and yaw should also be simple terms. So what the mixer does is it literally is the code that mixes your roll, pitch, and yaw PID sums. So the PID sum is the addition of P, I, and D, and it also mixes the throttle into all of that. So we have these tables of mixers, these arrays, really matrices if you want to think about it that way, but really what's going on here is we have 4 different numbers, and these 4 different numbers relate to throttle, which is the first number, roll, pitch, and yaw. And what it's really doing is it's telling how the PID sums should mix and the throttle should all mix into the motor output. So this is saying that for each motor, give it full throttle input, just scale throttle to it. For this rear right motor, give it a negative roll, positive pitch, and a negative yaw. So you'll notice that for the rear motors, which are this motor and this motor, that the pitch is both positive, because the rear motors, that's in the back of the quad. If you want to do a front flip, then your PID sum is a positive push. And then you'll notice for the front motors, these two, that it's negative. You want to spin down the motors when you have a positive pitch PID sum. And same for roll, you can see that the 2 right motors, they make the quad roll to the left, which is negative. So when you're given a positive roll, lower the motor output. And if we're rolling to the right, for the left motors, we want to increase the output. And same for yaw. It's quite simple. This mixer literally defines how the motors should act together in order to spin the quadcopter the way that we want it to, as well as mixing the throttle into there. So what I'm going to show you is the current mixer code, and that's found in this function here, mix table. And so here's the real meat of it. It starts off with this function here, this loop. Now this for loop goes through each of your motors, and it adds your roll PID sum, your pitch PID sum, and your yaw PID sum times the sign that they are. So if it's roll, it's roll PID sum times the roll sign plus pitch times the sign, and yaw, yada yada. It continues. And that gives your motors a basic output value. Then what we do is we find the maximum motor and the minimum motor, and that's used for certain cases where we run into trouble. And if we don't run into trouble, this is essentially all that happens if the motor outputs don't run into any trouble. So we continue down here, which is where we run into cases where we might have trouble. So what we do first is we find what the motor mix range is, and that range is what the minimum motor output is, the difference between the max motor and the minimum motor. And that difference, if it is greater than 1, then that means that the greatest difference we can realistically have is one motor at full throttle, which is 1, and one motor at min throttle, which is 0, and that difference would be 1. And so if the difference is greater than 1, then some motors are greater than 0. I mean, greater than 1, and some motors are potentially less than 0, or a negative value. And we don't want that. We want all the motors to be scaled between 0 and 1. So what we first do is we find what the range is, and then we divide each of the motors by the range. And by dividing them by the range, this gives us all the motor outputs within a range between 0, but it rescales the range of the motors so that the range is now 1. So that the difference between the max motor and the min motor is 1. Once we've scaled the range, we then have to play with the throttle, which is what we do with air mode. However, this bit of code really shows us what air mode does and how it tweaks the throttle. Because if you noticed, the throttle wasn't mixed in with the other outputs when we got this motor mix. It was just the roll, pitch, and yaw PID sums and how they affected the motor. What happens here is throttle is then taken and it's constrained so that the minimum motor and the maximum motor can never go greater than 1 or less than 0. So if the minimum motor is less than 0, we'll make sure that throttle is at least bigger than that. And if the maximum motor is quite close to 1, then we'll make sure that this throttle never allows the motor to be greater than 1. Because if it would be greater than 1, we will lower the throttle such that the motor cannot be greater than 1. And you'll see in this function apply mix to motors, we take that motor mix that we found before, and we take the motor output min, so that's like our idle motor speed, times the range. So the range is 0 to 1, subtracting the min. So really that's the range that the motor can move. So if you've stuck a motor limit, then that range will be different. And then it has a sign which just deals with reverse motors or not, and then we're just left with the motor mix plus the throttle, because that throttle mixer is always 1. So we're left with, when we come here, the idle plus the motor mix plus the throttle. So air mode is really just a fancy way of moving the throttle around to allow the maximum movement of the motors. Because if you look past here, past where we add the throttle, we then will come here and we'll make sure that all the motors are within the maximum and the minimum value. And without air mode, you'll run into times where it has to clip throttle values, or where it has to boost some throttle values that might be lower than 0. With air mode, you kind of get away from that. However, you do run into the problem where, in order to do that, it makes your motor output kind of jagged. Like you can see there's rough, it's not a smooth transition across this face. This curved face is smooth. It's a continuous curve. This, however, is jagged, a lot more sharp, and that can add some motor noise and other problems. So now if I switch branches, I can look at the mixer code that I've recently been working on. And now the basics of it are the same. The mixer, how we mix the PID sum to the motors, that stayed the same. However, how we then scale everything and deal with these bad cases of motor outputs is different. Now to begin, we originally mixed the throttle in with the roll, pitch, and yaw to give us this motor mix. And we also find what the max and min motor value is. That's the first thing. And then if the range is greater than 1, so the difference between the maximum motor and the minimum motor is greater than 1, then we have to rescale the outputs so that the range is now 1, which is what this code does right here. And if you remember, that sounds quite similar to how the old mixer does it. However, throttle has been mixed into this as well. Then what we do is we figure out how much we need to reduce the motors. And so before we had the throttle that would move around to try and keep all the motors happy. Now we find out how much greater the maximum motor or how much below the minimum motor is, and we use that to find how much we need to either boost in this situation or shrink all the motor outputs. So we scale things a bit differently here. Throttle's not added separately, it's mixed in with all of this. And then if the motor range isn't greater than 1, which is most of the time, we look and try to see if the highest motor is greater than 1, so it wants to be an output that is past full throttle, or if it wants to be an output below 0 throttle. If it wants to be above max throttle, we find how much we need to shrink it using this, which will make the max motor exactly equal to 1. Or if the minimum motor is less than 0, we find the amount that we need to boost all the motors to raise that minimum motor to be greater than 0. Pretty simple. And then we run some code here, right here, where we take all the motor outputs and we add or shrink all the outputs. Now what that's able to do, because of the new way that we're mixing the throttle, is really give us a much smoother and nicer output than we've had before. And what else we've been able to do using this new mixer is come up with an entirely new way to change the motor outputs. So to do that, we have this transient motor mix. Now full credit goes to Silverware, especially Sil F4ware, the new F4 version of Silverware, for coming up with some of this. It's really quite nice and cool. They came up with this mixer. I've modified it a little bit, and they came up with this transient mix, which I've also very slightly modified. It's similar, not quite the same. Yeah, so this transient mix is really a way of smoothing out the change in your motors without really giving you any downsides. And the way that it does that is we take your PID sum and we find what the change in your PID sum is. Using this, we find the change in your PID sum and we give it a multiplier. And we find the change in your PID sum for roll, pitch, yaw, and then we find what the maximum value of the change in your PID sum is. So the times where your PID sum is going to be changing the most, that'll be quick throttle, not quick throttle, quick flips when you just bang the stick, or really bad prop wash. Those will be times where your change in PID sum will be the greatest. What it does here is we then filter that value, that maximum change in PID sum, we filter that, and that gives us a number, which we call the Transient Mix Increase limit. What we then do with that is, if the Transient Mix Increase limit is greater than how much we would need to change the throttle, then instead we swap that with the Transient Mix Increase limit, because this is bigger. Now what that's going to do is it's going to reduce how much we're changing the motors, so the motors aren't going to reduce and change as quickly. And what's really nice about this is, if you're just doing a quick flip, instead of your motors instantly going from, say you go to do a flip, you give it full throttle, you bring the throttle down to 0, your motors are pretty much idle, and then you do a flip, Well, you'll have some motors instantly going to full throttle, and with this it'll smooth out that change a little bit and prevent it from just being so instantaneous, because your throttle can't, your motor can't go from 0 to full like that anyway. So this just really smooths out your inputs and gives you a smoother feeling quad. Something else nice that it does that I've noticed is if you're really the kind of pilot that likes to do these really popping kind of movements where you hold a line and then you kind of pop out of it and do a roll or a yaw, and you're really just locked into that axis and you're just popping your moves. By having a low transient mix filter value and a higher transient mix multiplier, you can really lock in your popping kind of tune while you're flying. It just really can lock in that axis and then just pop out of it, and it feels really nice, and it's a different feeling than I've ever had flying a quadcopter. But anyways, these transient mix multiplier and the filter value, those are still being played with, but what I found that I liked the most for my flying style is I liked the mix at 2000 and the filter value at 25. If you want to fly more with that pop-in kind of style, I found that 1 Hertz or even 2 Hertz for this filter on the transient mix increase limit is really nice for that, and I actually quite liked that as well. It was a nice difference. Lastly, what I want to discuss, the last thing that I added here, that's thrust linearization. And after I flew this code, I thought and felt that that might be quite nice to have, is some way to linearize your motor outputs, and I think that might help this mixer a bit more as well. So that's been added to the code. And lastly, I just want to point out how different my tuning's been using this new mixer. It might sound quite similar to the old mixer with a few tweaks. However, first I'm going to talk about the benefits that I've found. I found that my motors are cooler, that I have cooler motors. I've got a nicer kind of different feel to things. This handles bouncing off of the ground a whole lot better. This, if you've been wanting launch mode in EmuFlight, you don't need launch mode. With this code, I just arm and I can just move my quad into the position I'd want to for launch mode, and it just holds it. It will not move with this new mixer. It's really, really cool to see. It's just solid how it does things here. Yeah, less noise, so I've actually reduced my filtering a ton. I'm using a lot less filtering than I was before, and my motor noise is still less than using the old mixer. It's crazy. A lot lower motor noise, even lower gyro and D-term noise, just because of that lower motor noise. That all comes from this new mixer. Some of the differences and oddities I kind of found was my D-term wanted to be a lot lower, and by wanted, it's more needed to. If my D-term was too high, I could hear audible D-term oscillations. And when I reduced my D-term, those completely went away and it was fine. And the difference in tune, for example, before I was using this code, my tune, I had about 70 P and about 35 D. Once I used this code, my P was 90 or even higher, and my D was in the low 20s. And that's what I found to work really well. Like, those ratios are way different. Before, my D was about half of my P, and now my D was closer to a fourth to a fifth what my P was. So this code, just because of how it works and how it was doing things, I needed a lot less D, yet it was still handling things very nicely. I was very, very pleased with this change. Yeah, the mixer's working very well. You crash into things, you'll be surprised at how well it handles crashes. Same as bouncing off the ground. If you ever land and your quad just wants to bounce around on the ground, it is a lot better at handling that. Before, my quad would kind of freak out a lot more. With this, it's much more minimal. And yeah, so when you're flying this and tuning it, play around with the transient mix and the transient mix multiplier. So the transient mix hertz, which is the filter value, and that multiplier. And as well, you will most likely need less D term, probably a bit more P term. But once you get this dialed in, it is a whole different beast. It's awesome. I think that a ton of you are really gonna like this. And yeah, that's all I've got to say about the mixer and the changes that I've done, and I hope that you all enjoy that. Have a good one, everyone. Thanks for